In this video, I'll provide more details about decaying exponentials. In particular, I'll talk about how to estimate the time constant from measured response data and how to use the time constant as a system design parameter. This is the form we'll use for decaying exponential functions of time. The value of the function starts out at y0, and the function decays exponentially as time increases. In an exponential decay, the rate of change, or the slope of the function, is large for small times and gets smaller as time increases. The exponent depends on the time constant, represented as the Greek letter tau in this equation. If tau is large, the function decays more slowly than if tau is small. The exponential constant e is just a number. A number can only be raised to a power that's also a number. It doesn't make sense to have an exponent that has dimensions or units. Therefore, the exponent, negative t divided by tau, must have no units. This means that since units of time are seconds, the units of tau must also be seconds. Next, I'll introduce some more details about the effect of the time constant on the rate of decay of the exponential function. Mathematically, the form of the exponential function we'll use is here. E is the exponential constant. It's an irrational number that's approximately 2.7183. If the exponent in this function, negative t divided by tau, is equal to negative 1, e to the negative 1 is approximately 0.368. So if t is equal to tau, the exponent is negative 1, and we multiply the original value of the function by 0.368. This means that the value of the function at time tau will be 0.368 times the initial value of the function. In fact, anytime we increase t over tau by 1, we get a multiplicative factor of 0.368. That means that if the value of the function at some arbitrary time is y1, the value of the function at a time tau later will be 0.368 times y1. This is equivalent to saying that the function's value decreases by about 63.2% every tau seconds. These relations allow us to estimate the time constant from a plot of the exponential function. If we can measure the response of the output of the system that has an exponential response, we can estimate the time constant for the system. I'll do that next for the case of a cooling frying pan. This is the data representing the frying pan temperature as a function of time. The frying pan temperature is being measured by using a thermistor in a Wheatstone bridge. The output voltage from the bridge circuit is used to indicate temperature. Initially, at room temperature, the output voltage is 0, which is the operating point. During this time period, the heat under the pan has been turned on, the frying pan is warming up, and the voltage is increasing. Somewhere near this time, the pan is removed from the heat source and the pan starts to cool. During the cooling time, the pan is dissipating energy and the temperature decreases exponentially. Our goal is to estimate the time constant and the equation governing the curve during the heat dissipation process. We know that for an exponential function, the value of the function decreases to 0.368 times its initial value over one time constant. The initial time is arbitrary. I'll choose it to be at this point. At this point, the voltage is about 1 volt and the time is about 200 seconds. One time constant later, the voltage will be at 0.368 volts, which corresponds to this point on the curve. The time at this point is about 400 seconds, so the time constant is the difference between those 2 points, or approximately 200 seconds. Now I can write the equation for the curve. Temperature as a function of time is equal to the initial temperature, 1 volt, times e to the minus t divided by tau, 200 seconds. Notice that the value of this function at time t equals 0 is 1. This function is based on redefining the time at this point to be 0 seconds. This definition changes if we choose a different value for the initial value of the function. I introduced the general idea of why the time constant is important in the introductory video for this chapter, but I want to revisit it here after I've used a set of data to estimate the time constant. Equations governing systems that store energy are called differential equations. I'll talk more about these types of equations later in this class, but the basic idea is that differential equations govern the rate at which the energy in a system can change. A general differential equation for a system that has one energy storage element, such as our frying pan, is shown here. If the differential equation has this form, you only need to know what the time constant is in order to estimate the differential equation. So if you measure the response of the system to some initial energy storage, you can estimate the time constant as we did with our frying pan. This gives you an estimate of the differential equation itself, which can then be used to simulate the response of the system under other conditions or to perform system design. The process is very similar to what we did for linear systems. We used measured data to estimate the slope and the y-intercept of the equation that described the component's operation. That equation could then be used to estimate the system's response under other conditions, or to design a system containing that component. Next, I'll talk about using the time constant for system design. The approach here is also very similar to the design process we used for linear systems. In linear systems, we had an equation describing the system operation in terms of the component values for the system. Then, given a mathematical relationship in terms of the slope and the y-intercept that the system should implement, we could choose component values that provided the desired relationship. The only difference here is that the mathematical process to be implemented will be based on the time constant, since in energy storage we're interested in how quickly the system responds, which is characterized by the time constant. The example I'll use to illustrate this is an electrical circuit consisting of a resistor and a capacitor. The capacitor stores energy as a voltage difference, while the resistor will dissipate energy as heat. So if I charge the capacitor to some initial voltage V0 and then close this switch, that initial energy in the capacitor will dissipate through the resistor. The equation governing the capacitor voltage will be V of t is equal to V0, the initial voltage, times e to the minus t over tau. For this system, the time constant is equal to the resistance of the resistor times the capacitor's capacitance. We want to choose values for R and C to get a desired time constant. Our design problem is to pick values in this circuit of R and C such that the time constant is 2 seconds plus or minus 10%. So at any time constant between 1.8 seconds and 2.2 seconds is fine. So if I choose a capacitance of 10 microfarads and a resistance of 200 kiloohms and multiply those two numbers together, the time constant is 2 seconds, which is exactly my requirement. Now, keep in mind that the individual values of R and C don't matter. It's the product between the two. So let's say I pick a C of 220 microfarads and a resistance of 10 kiloohms. Now, if I multiply these two together, I get a time constant of 2.2 seconds, which is just barely within my requirements. So let's go wire up these circuits, measure the time constants, and see what actually happens physically. This is our 10 microfarad capacitor, and this is the 220 kiloohm resistor. I'm applying 5 volts across this combination with this red wire and black wire. I'm using channel 1, the orange wires of my USB-based oscilloscope, to measure the capacitor voltage. Let's start acquiring data. Initially, the capacitor voltage is 5 volts. Now if I unplug the red wire, the capacitor voltage starts to decay exponentially. It's gotten to about 0, so I can stop data acquisition. Now, the time constant is when the voltage reaches 0.368 times its initial value. I can find that point with a cursor very easily. So 0.368 times 5 is 1.84. I can get the time elapsed with cursors on the x-axis. So there's where I turned off power. And here is where it gets to 1.84 volts. That time is about 1.89 seconds. It's not exactly what we expect, but it is within the requirements. Now let's take a look at the 220 microfarad capacitor with the 10 kiloohm resistor. Here's our 220 microfarad capacitor and our 10 kiloohm resistor. The connections here are the same. I'm applying 5 volts across the capacitor with the red wire and measuring the capacitor voltage with the orange wires. Let me start acquiring data. So the initial capacitor voltage is 5 volts again. If I unplug the red wire, that capacitor voltage should decay exponentially. Okay, I'm going to stop data acquisition, set up a cursor at my value of 1.84 volts. Which is about 0.368 times 5. Now, measuring the elapsed time, there's about where I unplugged the red wire, and one time constant is about 2.3 seconds. So I don't quite meet my requirements with this combination. When thinking in terms of exponential functions and time constants, keep in mind their relationship with the governing equations for systems that store energy. Energy storage and transfer are really important to engineers, so we tend to see exponential functions a lot.